To a new video of a heat transfer. Today we talk about natural convection, also called free convection. So there is motion of a fluid, but this motion is not induced by an external agent, for example a fan, a pump, or a compressor. In those cases we talk about forced convection. Instead, for natural convection, the motion of the fluid is induced by the temperature gradient itself. Usually in free convection, the convection coefficient is smaller than in forced convection, and generally in liquid fluid flows the H convection is larger than in the motion of gases. So let's imagine, for example, a hot body like an egg sitting on a table, and the environment of the kitchen is cold. So we don't force any motion of air around the egg, and we let the egg cool by itself. Since the surface of the egg is quite hot compared to the environment, then the temperature of the air around the egg gets warmer. And since the temperature increases, the density of air around the egg decreases. Therefore, the egg around will warm the air, and the air around the egg gets lighter, and therefore it starts moving upward. And by continuity, then the hot air at the larger distance from the egg will move down. Therefore, there is an induced fluid motion, and the egg cools down because of the air motion, but it cools faster than if the air were still. So we can represent this sort of feedback mechanism in the following way. We have temperature gradients. This temperature gradient induces some density gradients because for a gas, air density are related. Since we have density gradients, then because of Newton's second law of motion, then these differences in densities will induce a motion. So this motion will have an impact on the energy balance through convection, and the energy balance itself will feed back to the temperature gradients. In free convection, the velocity field must be found together with the temperature field, whereas in forced convection, in most of the cases, the velocity field is given. An important quantity in free convection analysis is the coefficient of thermal expansion, that's defined as beta equal 1 divided by the volume times the partial derivative of the volume with respect to the temperature at constant pressure. For a gas, then this expression reduces to the following form. So you have 1 divided by the density with the minus sign, multiplied by the ratio of the differences between the density at large distance from the surface minus the density divided by the difference between the temperature at the far location from the surface minus the temperature. So the coefficient of thermal expansion is a property of the fluid, and it tells us how much the volume changes if the temperature changes at constant pressure. So we can represent this schematically in this way. This quantity beta is important because it enters the mathematical description of natural convection. So let's study natural convection in a boundary layer. So we take a case where we have a laminar flow. We assume the Prandtl number to be about 1. So the heat transfer effects will be comparable with the diffusion of momentum, so the thickness of the thermal boundary layer will be comparable with the thickness of the velocity boundary layer. So we imagine a plate, flat plate, positioned vertically, so that's a hot temperature, whereas the environment is at a colder temperature. And we define the temperature of the wall as Tw. And we also assume that we know the pressure, the temperature, and the density of the fluid at a large distance so in the free stream from the surface. So we can already imagine that there is going to be a motion because of buoyancy effects in the vertical direction moving upward. So there is a temperature gradient here. So that's the thermal boundary layer. That's when the temperature changes. And we also have a velocity boundary layer. And note that now the temperature gradient are confined within the boundary layer, so in a region close to the surface, and the velocity goes to 0 in the free stream. We assume that delta, the thickness of the boundary layer, is thin. So this means that the partial pressure of partial y is equal to 0. So the pressure only depends on x. Therefore, we can define as dp dx. So we don't have a partial derivative sign anymore. We just had as a standard derivative. And that's equal to dp infinity dx. We also assume that the fluid outside the boundary layer is stationary, so we can have a relationship between the pressure gradient and the rho infinity times the gravity. So we know everything, we know the balance, it's a static balance of the fluid outside of the boundary layer. So now we can take a look at the momentum equation under the boundary layer assumption. And so the momentum equation in the x direction is nothing but the Newton's law of motion, the second law of Newton, written in differential form. So in the left-hand side here, we have the acceleration, and this is the steady form of the acceleration. It involves the partial derivatives of velocity with respect to coordinate x and y. And the right-hand side, we have the sum of the forces. So we have the stresses due to viscosity, and then we have the effect of the pressure gradient and the effect of gravity. But we also know that the pressure gradient only depends on x, and we have stationary condition in the free stream. Therefore, we can eliminate this partial p partial x, and we express this pressure gradient as a function of the density in the free stream. So we arrive at the second expression. Furthermore, we assume that the gas is an ideal gas. So we know the relationship between the density and the temperature. We introduced beta, the coefficient of thermal expansion that we talked about before. And in this way, we eliminate the density. So we have a velocity u and v, so where u is the velocity in the stream y direction and v is in the wall normal direction. And we have the temperature and we don't have the density. But the x momentum equation is just one equation, but we actually have three unknowns. So the two velocity components, so the u component in the stream y direction, so in the vertical direction, following the plate, parallel to the plate, v in the wall normal direction, and the temperature. So we need two more equations. One equation is continuity equation, so that defines the conservation of mass, and then we have the energy, so that defines the transport of the temperature. So we have a convection term that's equal to the heat conduction term. And we write here the x momentum equation again. So this is a steady, two-dimensional, laminar dynamics. And so we have three equations and three unknowns. To solve this system, we need boundary conditions. So at y equals 0, so on the surface of the plate, the velocity components u and v are 0 because of no slip condition, and the temperature is equal to Ts. Actually, I call this Tw in the drawing, but it's the same thing. So it's a given specified temperature at the wall. As we move away from the plate, then as y going to infinity, then both velocity components go to 0, and the temperature approaches the temperature in the free stream. So this problem is well posed. So we have three unknowns and we have three equations, but it's still very simplified. So it's, as we said, it's a laminar case, it's two-dimensional, it's steady, But in cases that are interest for industrial applications, of course, we have to rely to experiments and rely on computation for example, cases on three-dimensional or unsteady and in general turbulent flows. It's important to write the X momentum equation in non-dimensional form. So we introduce a new non-dimensional number called the Grashof number. So to do so, we introduce X dot, Y dot, U dot, V dot, and T dot. These are non-dimensional quantities. So for example, X dot is the coordinate X divided by a characteristic length LC. So for example, for a sphere, it can be the diameter. For the boundary layer case, it could be the length of the plate and so on. Whereas the velocity components are non-dimensionalized by a characteristic velocity. And the temperature and scaling assumes this form. So what we do now, we take these new expression, this definition of non-dimensional quantities, and we substitute it into the momentum equation. So a little bit of algebra, that's a good exercise, and we find the equation in non-dimensional form. So for example, the convection terms only involve U dot, X dot, V dot, and Y dot, so it's non-dimensional. On the right-hand side, we have also non-dimensional terms, and we have this new non-dimensional number, that's the Grashof number, and the Grashof number represents the ratio between buoyancy and viscous effects. We note here we also have a Reynolds number, and here in the buoyancy term, we have the Reynolds number squared. So we can compare the Grashof number with the Reynolds number squared to see how important is the convection term, the buoyancy term in the general free convection. So if the ratio between the Grashof number and the Reynolds number squared is much smaller than 1, then natural convection is negligible compared to forced convection, whereas instead the Grashof number divided by Reynolds number squared is much larger than 1, then natural convection dominates over forced convection. If the Grashof number divided by Reynolds number squared is order 1, actually mathematically it would be more correct to write it in this way, order 1 with the equal sign, then natural and forced convection both play a role in the dynamics. As a final step, of course, after understanding the physics, we need to find ways to compute H, natural convection coefficient. If you remember, in forced convection, the Nusselt number is a function of the Prandtl number and the Reynolds number. In natural convection, the Nusselt number is a function of the Grashof number and the Prandtl number. And in most correlation, these two quantities appear next to each other, so they can be multiplied, and we define a new number called the Rayleigh number. And usually the correlations are expressed in a similar way to the forced convection ones. So Nusselt number is equal to a constant C times the Rayleigh number to the n power. So C and n depend on the geometry, on the flow regime, on the roughness, and on many other things. And in general, n is equal to 1/4 in laminar flows and to 1/3 in turbulent flows. So you can look in books for different correlations and depending on the geometry of the flow regime or the problem you have to solve. Okay, thanks a lot. I see you next time.